Hello everybody. It's been quite a while since I made a video like this. I think it's about 10 years or 11 years. And I'm doing this because I want to share with you my fresh impressions that I've got from reading a second time Heaviside's works. Um, I just finished reading them all. So Electrical Papers, 2 volumes, and electromagnetic theory. His electromagnetic theory, 2 volumes, 4 volumes. Some of the things are overlapped, so I had to read them twice. I read Heaviside a while ago. I think it's been more than 10 years, but I it's a tough read. So yeah, the fresh impression that I get is that um, the research that I'm doing is on the right track. So um, the conception of light and radio waves as electromagnetic waves is simply not true. It's simply not true. It's a false path of research. Is a false uh, theory. It is a wrong theory. It is a misleading theory, and it is holding us back. It is holding us back from a lot of things that can be done once the nature of light and radio waves is understood. So the crux of the matter. So I'm going to tell you what I've got from reading Heaviside anew, is that, oh, and by the way, you know, I think you know that Heaviside was the among the first, if not the first, who took Maxwell's treatises of electricity and magnetism and analyzed them and put them in order. And he is the one who came up with the so-called Maxwell's equations. He was the one who wrote them in vector form. He was the one who set up the vector calculus and algebra together with Gibbs in the US, Willard Gibbs. And so they worked in parallel. Actually, Willard Gibbs was more into vectors than Heaviside in the UK, because Heaviside had to deal with the issue with quaternions, and which contained imaginary numbers and vectors, and it was a mixture of mixed algebra. So anyway, in the end, it looks like Heaviside realized the importance of working only with vectors, dropping all the imaginary numbers from calculations, and wrote Maxwell's equations in vector form. Now, I heard people saying that while doing that, Heaviside simplified and left out a few details that were in Maxwell's theory. I'm not aware of any details that have been left out. All I can say is that uh, Heaviside wrote in his books that he preferred to work with magnetic field and electric fields, with the vector fields, and not with the potentials. So the only difference that I saw between Maxwell and Heaviside was that Maxwell worked with potentials. He expressed the magnetic field and the electric field in terms of potentials, and Heaviside chose to work instead of potentials for expressing the magnetic field and the electric field. Instead of working with potentials, he chose to work with vectors. So instead of expressing the intensity of the electric field, for example, in terms of a potential, he worked directly with the electric field. And in terms, instead of expressing the magnetic field in vector form, in its components, Maxwell used the magnetic field expressed in terms of another function which he called the potential of the magnetic field. Now, here there is a problem, and Heaviside has discovered that a mistake in Maxwell's theory, and he points this out, that Maxwell made a mistake of expressing the magnetic field as the gradient of a scalar function. As you know, this is wrong. Now, in Maxwell's equations, you can see that, you don't see that, you see the magnetic field expressed as the curl of a vector field, the magnetic potential, the A, if you know the symbol. So B is the curl of A. While Maxwell, in his treatise, expressed the magnetic field as the gradient of a scalar function, which he called magnetic potential, and this is wrong. So I'm not aware of anything that Heaviside has left out from reading Maxwell, and besides that, he clears out the main concept that makes Maxwell's theory into an electromagnetic theory of light and radio waves. And this is the famous displacement current. This is the famous displacement current. Even Heaviside says it clearly, that what makes Maxwell's equation, what turns Maxwell's equations into the equations of a wave is, or waves, magnetic waves and electric waves, is the concept of displacement, electric displacement. Now, there is a lot of ambiguity there. He acknowledges it. He even says he doesn't understand the nature of this displacement current. And of course, he doesn't even discuss the physical nature of the electric field and magnetic field. He doesn't say what they are. They can be vortices, they can be just lines in, but he mentions ether. So it's a motion in the ether. These two fields correspond to motions in the ether. Now, what's important here is that while working with these notions, which they didn't even define clearly in terms of their physical nature. Okay, so they worked with this electric and magnetic fields and the displacement current. They assumed, and I wanted to be very, very careful here, because this is where they, Heaviside and Maxwell and those who came after, including Hertz, made the mistake of believing that what they saw in Maxwell's equations, and especially the electromagnetic waves that come out of those calculations, are valid for vacuum. Okay, so the crux of the matter being the displacement current, I want you to realize what they're talking about in terms of when they discuss the displacement current. When they discuss the displacement current, they take a capacitor, parallel plate capacitor, and they imagine what's happening in the space between the plates when you apply a voltage to the plates of the capacitor. Of course, there is going to be, because you start with a zero voltage and the capacitor is discharged, you start with a increasing electric field because the charges accumulate on the plates, and you start from zero, so you get an increasing electric field, an electric field that increases in time. And then when the current, the charging current stops, the electric field remains constant, remains there in the capacitor and remains constant. What they're saying is that in the space between these plates, there is a displacement current. What does this mean? It means that normally, be careful here, normally, in the space between these two plates of the capacitor, normally they insert matter, an insulator. It can be a solid insulator like glass, rubber, water substances. They've been using a lot of insulators in the past, uh, and or liquids like oil, for example, yes, which are polarizable, meaning that when you apply an electric field, if you place that substance between the plates and you apply an electric field, the charges will be displaced. They will not travel like a normal electric current between the plates because it's an insulator. But charges will be displaced, the charges that are in the substance, and can be displaced. And this movement of charges in the space between the capacitor, the plates, this movement of charges will be continuous as long as the electric field is increasing or decreasing in time or changing in time. So I agree with this. When you have an electric field that is constant, the charges will be displaced and will stop. But if the electric field is changing in time, then the charges will be slowly moving up to a maximum point and then they will stop. This small movement, this small displacement of the charges in the space between here in the dielectric substance will create a current. I agree with this 100%. And this electric current will produce a magnetic field. Yes, this is true because it obeys the laws of electromagnetism. Charges in motion produce magnetic fields. I believe that this magnetic field that will produce in the space between the plates will be much weaker than the magnetic field that you will see in the wires that are charging, through which the charges are moving from the power supply to the power plates. So the displacement of the charges that happen here are so small, I think, compared to the current, the charging current that is charging the capacitor. Compared to this current, the current that you see here, while the electric field is increasing in time, is so much smaller, and will create a magnetic field so much weaker than the magnetic field that is produced by the charges flowing through the wires. Now, pay attention to this, because this is where the things get wrong. Now, imagine you have vacuum between the plates. You still have a changing electric field between the plates. Now, vacuum is not polarizable, and they made this assumption that even vacuum is polarizable, meaning it's made of charges that can be displaced. So they claimed that this capacitor, even in vacuum, will have, besides the changing electric field, the electric field increasing in time, besides this electric field changing in time, increasing in time, there will be charges displaced like in a normal dielectric, like in glass, like in rubber. In these modern days, you would say even in plastic, right? And that these charges, which we are in vacuum now, these charges that are supposed to be in vacuum, yeah, they assume that the vacuum is polarizable. Okay, these charges will produce a magnetic field while they're moving, while the electric field is changing, increasing or decreasing, and they will produce a magnetic field. Yes, so this is the crux of the matter. If you believe that the vacuum is polarizable, that vacuum has positive and negative charges, and that the electric field can separate these charges, then you go on and you will be okay with Maxwell's theory and with the fact that the radio waves and light are electromagnetic, because this will make the theory work. But what I'm saying is vacuum is not polarizable. It doesn't have charges. Think about it. Even very weak electric fields, even very small voltages are supposed to be able to polarize the vacuum. We should be able to see this, and we're not seeing it. It's not possible. It's not happening. If vacuum would be polarizable, imagine you have ions in between here. In vacuum, you would be able to separate them. You would be able to make them move. You'll be able to get an electric current. If you apply a constant voltage, they will be able to move. You'll have electric currents moving, like in electrolysis. So this assumption is at the basis of Maxwell's theory. So in vacuum, if you don't believe, like I do, that vacuum is not polarizable, that doesn't have charges, then for you and for me, and for those who refuse to make this assumption, for you and for me, electromagnetic theory is not true, is not happening. It's not happening. So this is a very important point, because this theory is actually holding us back from thinking about the real nature of light, the real nature of radio waves, of what's happening when you have an antenna. Imagine this is an antenna. This is the power supply. This is an antenna. And the current is moving up and down, right? It's an alternating current, high frequency, moving up and down. Now, electromagnetic theory says that the electric fields will detach from the charges and travel away, and magnetic fields produced by this current will always produce waves in the space and will travel away. And in here, in this vacuum, these electric fields and magnetic fields will induce one another. This is what they're saying. And this is wrong for the reasons that I told you. It's not happening in vacuum. If you believe that the vacuum is polarizable, then it's fine, and you go on with the mainstream, and the electromagnetic theory is the thing for you. But it's not happening. I'm warning you that you are on a wrong path. So what's happening in the case when the vacuum is not polarizable is that the charges moving up towards the tip, they accumulate towards the tip, right, when they go up. And at the moment when they arrive here, right, because they accumulate in such a great quantity, they push on the ether and it produces a compression. Then they travel down, then it produces a rarefaction, and when they travel up, they produce another push, and they travel down with high frequency. Actually, there is a distribution of the charges. Not all of them will gather up at the very top. There's going to be a curve here, but this accumulation of charges is what pushes on the ether and produces compression waves and compression and rarefaction in the ether, which produces waves of compression and rarefaction in the ether, longitudinal waves in the ether. So this is what we should be looking at. This is how we should be thinking about radio waves. Radio waves and light waves are not electromagnetic. They are longitudinal waves in the ether. And if you pay attention to this detail, I suspect you'll be able to, this is a great potential to make huge advances. For myself, I can tell you for myself, once I came up to this realization, I just filed a patent on an application of this theory. Because can you imagine if radio waves are waves of compression and rarefaction, and you are able to produce stationary waves. Imagine stationary waves between an emitter and a reflector. Here in this space, you produce stationary waves. Then these stationary waves will be made up of ether moving backwards and forwards and producing nodes and antinodes, which are points of rarefaction and compression that are localized, right? The points of rarefaction and compression will have gradients in the ether pressure between between the regions in the stationary waves. Look them up. Look up the physics of stationary waves, and you will see what I mean. So these regions of between nodes and antinodes are regions of ether pressure gradient, and that's where you obtain gravitational fields. That's where you obtain gravitational fields, because if you have an ether pressure gradient, you have gravitation. This is what gravitation is. And this is what my patent is saying, but I believe there are more applications to be discovered. You can think of even propulsion. You can think of using them in the same way as you're using acoustics. The only thing that remains to be clarified here is how can you get polarized. What's the polarization of light? What does it mean? And radio waves can be polarized. So what is the physics? What is the nature of polarized waves? Because if you have longitudinal waves, this is the remaining issue. If you can come up with a mechanism, and I'm working on this myself, but I'm sharing this for you. If you can come up with a mechanism in which longitudinal waves can behave as polarized waves, which means if you send them through a polarizer and then you send them through an analyzer, they'll be cut off, and if the polarizer are parallel, then they will travel through, but if they are crossed at 90 degrees, they won't be able to travel through. And the mechanism of polarization by reflection and by diffraction, this is by transmission. If this mechanism is cleared up, everything falls in places in its own place. The best thing to do is to work with sound. If you can polarize, I tried it. I think I got something, but it wasn't a very clear result. So these are the issues, and that's why I'm making this video, to make you aware and to urge you that if you're looking at something to push you forward, to allow you to make some progress, some discovery, it is this. Realize that light and radio waves are longitudinal waves in the ether. Okay? And speaking of which, the last thing that I wanted to say is that in my latest work, Fundaments of Theory of Ether, Part 4, I have described all these things. I'm going to put a link in the description of this video, and I want to be very clear what I mean. What I mean by radio waves and light being waves of compression and rarefaction in the ether, longitudinal waves in the ether. What does this mean? This means that the ether moves forwards and backwards along the direction of the propagation of the wave. Now, along these waves, you're going to have ether moving backwards and forwards, and while doing that, you're going to have regions of compression and regions of rarefaction. Of course, they move with the wave longitudinally parallel to the direction of the wave. And what we call the wave front is going to be normally the regions of compression. Now, I told you what is the interpretation of the regions of compression and rarefaction in the wave. The compression is higher pressure of the ether, rarefaction is low pressure in the ether, and the space, the interval between them is in the interval between them you have an ether pressure gradient, which means you have gravitational field there. It's a mini gravitational field depending on the intensity of the wave, of course. So these compressions and rarefactions are micro gravitational fields. That's why I call them electrogravitational. So radio waves and light are electrogravitational fields. Because of this, there are gradients of ether pressure in along the wave, and this is what makes them gravitational. Why do I call them electrogravitational? Because this movement of the ether back and forth is an electric field. This is what is an electric field. You'll look in the paper and you'll see why, but basically what it is that the electric field is produced by a charge, right? Now, the nature of the charge in my work is that of a vibrating structure. It's a vibrating atom or vibrating electrogen or both, or just the atom itself, or just the electrogen if it's isolated, like you have it in thermionic emission when you have the electron beam and so on. So the vibration of the thing is what produces the electrostatic effects. So that's why the vibration of the structure is going to produce a backwards and forwards motion of the ether. And this is why, because the space surrounding a charged object is called electric field, then the vibration creating forwards and backwards motion in the ether, that's why the correspondence is that the motion of the ether back and forth is that of an electrostatic field, of an electric field. So going back to the picture of light and radio waves as longitudinal waves in the ether, the forward and backward motion of the ether is the electric part, and the compressions that this motion produce and rarefactions corresponds to higher pressure ether pressure and lower ether pressure than the average, and the interval between them will have an ether pressure gradient which corresponds to a very tiny gravitational field. If you can enlarge this area, this volume, and make it static like you get it in stationary waves, then you're going to be able to detect a greater gravitational field. And this is what my patent is about. It's submitted already. There are others. I think there are other things that can be done with this. I'm myself working on this, and I just thought about sharing this with you to make you aware of how important this is. And if you have time, if you are inclined to do so, if you think that there is something in this, give it some thought, some attention, and you'll get something out of it. I really believe that you'll get something out of it. So this is what I wanted to share with you. I'm so glad that I got a time to do this. I don't know when I'll do such a video again, because I'm not very I'm not good at, I don't think I'm good at making videos like this. So it's been more than 10 years, yeah, since my last video. And yeah, keep on reading, keep on thinking about what I told you, and I'm waiting, and I myself working on, when I have time, working on developing this theory more to bring it into more testable regions, into applications that can be made. And who knows, even propulsion. I think there will be applications in propulsion too, because there is, if you think about what's happening in acoustics, if you have acoustics, propulsion in acoustics, I'm not aware of any application, but if you can get an application, think about light and radio waves as basically sound mechanical waves in the ether, just like sound is in air, for you know. if you can come up with an application of this theory to propulsion, it's going to be huge. It's going to be huge. Okay, so I wish you all the best and much luck, and that's it. All the best.